Okay, so on to part two. So we've talked about collecting data and just how do we talk about data intelligently. And now it's time to actually examine. We'll start with numerical data and then we'll talk about what do we do with categorical data. But there's a lot more in numerical data, so that's where we'll start. So first thing you want to do, so once you have a data set, you'll want to see what's going on in there. So you want to get an idea of what this data looks like. And sometimes this data, or often data sets will be quite large. And so we use data visualization to help us visualize the data instead of scrolling through. That gets really tedious and it's hard to extract any information from just like looking at your data. So instead we use data visualization. And so the goal is to provide a clear and concise summary of your data. One thing that I do want to highlight here is that a successful data visualization should require minimal explanation. And so if you're ever having to generate some sort of data visualization, that's great. Um, just keep in mind that the more you have to explain it, the worse it is. So you want to have something that people can look at and just kind of glance at and understand what's going on, with a little bit of background about what information is being presented. But besides that, it should be pretty straightforward. And if it's not, you've probably overcomplicated things, and that's not really good. So I've got kind of good data visualization, or data viz, as we call it in the biz. And so I've got this beautiful, it's just called Facebook connections. And I mean, the people that have Facebook and Twitter and whatever, they're doing like crazy cool stuff. And so, of course, they've got this beautiful data visualization of Facebook connections. And yeah, pretty nice. But although this one looks pretty, right? When I'm looking at it, and I'm looking at it over here. When I look at it, I mean, cool, great. But then I start to kind of wonder, all right, so there seem to be two levels, and then there's some data points that are just kind of in between here. They seem to be connected by some rope or something or other, and what does that mean? Does the color of the bubble mean anything? Does the size of the bubble mean anything? I'm just left with so many questions here, and I'm sure that they have managed to pack a ton of information in here. There's no doubt in my mind that they were able to just cram everything in there. But it's not self-explanatory. And so for me, that would make a bad visualization, even though it's so visually appealing. But it's a bad, a dad. Well, it's a bad data visualization. Okay, so keep in mind, if you're producing some sort of visualization, then just kind of go back to basics and just keep in mind always that you should require minimal explanation. Right? Oh, I forgot I was in the notes. Okay. Let's see if I can grab this whole thing or what. So to visualize numerical variables, what we're going to use is called a histogram. And a histogram looks like this. So we've got bars and the height of each bar just denotes the frequency in your data. Okay, and so these kind of, well, they're called bins, and that's what they are, right? They're just little bins. So we've broken up our continuous line here, X, let's call it X1, into bins. So what happens is if you have a data point that's between 10 and 15, it goes in the 10 to 15 bin. We're essentially making categories, but not officially or explicitly, but it is kind of putting, a histogram does put numerical data into kind of temporary categories just to help us visualize the distribution. And so here we can see that there weren't very many points. Maybe looking at the scale here, it looks like maybe one or two were in the 10 to 15 bin. Whereas in the 20 to 25 bin, we have almost 35 data points, right? That's a lot. So here it's easy to visualize the distribution of the data. Okay, so we visualize the data to see the distribution of it. Okay. And so we've got these two distributions, two different data sets. These are histograms of randomly generated data. So I just told it to give me some random data here. Okay. And then we're going to refer to both of these histograms in a little bit here. But so same idea here. We can, usually whatever software we're using will have some default bin, and that's usually what I go for. I don't mess around with changing the bins too much. But if I was really interested in kind of the nitty gritty of how these things, what the distribution looks like, I could change the bins, maybe 10 to 11 bin and 11 to 12 bin, and so on. But I think it would break up our data too much. And usually the default is fine. I'm never disappointed. Okay, good. So let me see here. I'll just grab all of this here and then we can talk about it. Okay. So that's what was cut off here. One of the most common distributions is the normal distribution. And so I want you to kind of think about, so there are shapes for distributions, and just like you know what shape this is, right? You know what shape this is, okay? What I want you to start incorporating into your shape vocabulary is that this, if your histogram starts to look something like a bell shape, right? And you've probably heard about a bell curve before. If a histogram has this bell shape, we call it the normal distribution. Okay? And so this is the normal distribution. It doesn't have to be capitalized, but I like to emphasize that it's a name, only because it confuses a lot of people, right? Like normal is a concept for us, right? And so the new normal, no, but normal is a concept that we use all the time, right? But now we're talking about this normal distribution, and now it's the name of a shape. And so that's why I tend to capitalize it. Sometimes I don't. You don't have to, but I'm only capitalizing it to emphasize that it's a name. Okay. So normal distribution in general, right, has a single mode, and a mode is a peak of a distribution, right? So a single mode, so one peak, and it's symmetric. Okay. So here, right, we've got one mode and it's symmetric. And that's what makes up a normal distribution. So when we have any distribution, such as these histograms here, right? Now we have two distributions, histogram 1, histogram 2, or the distribution of x1 or the distribution of x2 if you prefer, but I'll just call them histogram 1 and histogram 2. When you are describing a distribution, to fully describe a distribution, you have to talk about three things. And so, and you always have to cover all three of these things. Okay, so what I want you to imagine is the easiest way to think about it is, okay, you're on the phone and it's a landline all of a sudden. Kind of banana phone here, right? You're on the phone with your friend and you're trying to describe this distribution. That is what we're doing, right? And so it's always kind of good to remind yourself of what you're doing. So you're on the phone and, oh yeah, I got this histogram 1 and yeah, so pretty crazy. Well, so your friend is curious, right? Oh, what does it look like? Oh, well, you need a shape, right? So first thing you have to talk about is the shape. Well, it looks kind of like a normal distribution, approximately normal, right? In either of these cases here. Oh, cool. Yeah, what else can you tell me about it? Oh, well, the first one is centered on like 25-ish, right? So when you're describing these, it's just on the phone. It's just rough approximations, just to give your friend on the other line, or on the other end, just an idea of what this thing looks like, right? You don't have to go into any detail, but you do have to say where it's centered. Okay, so where are the most frequently occurring data points happening? I don't know, around 25. Oh, how about a histogram 2? Let me check. Oh, also around 25. Weird. Okay, cool. Yeah, what else can you tell me about it? Well, okay, so you should probably know the spread, right? So we talk about the shape, we talk about the center, and we have to talk about the spread, right? The how variable, I'll start using that term now kind of loosely, how variable am I expecting my data to be if I collected more data? The dog's upset that I'm talking. And so the spread tells us kind of, it gives us an idea of what we're expecting to see. Oh, so the spread here is between 10 and 40 for histogram 1. Oh, but for histogram 2, it looks like it's from like -50 to 100. I just usually use those cutoff points that are visible. You don't have to, like this one, it goes a little bit beyond -50. That's okay. All right, we're just getting rough ideas, right? So in terms of the shape here for histogram 1 and 2 were similar, right? The center was roughly the same. And so the only difference here between histogram 1 and histogram 2 is going to be the spread, right? And so we'll have to take that into account, right? So to describe a distribution, we need to discuss these three things. In terms of the shape, I really just want you to kind of drill down to either it's a normal distribution or it's a non-normal distribution. So it is clearly not normal. Okay. And we'll talk more about non-normal distributions in a little bit here, but the center, just a rough kind of eyeball approximation. You're just glancing roughly where is it centered, right? Where is most of your data centered? And then the spread, again, a rough approximation. Later on, we're going to have numerical measurements for these. So this is just at a glance, looking at a graph and trying to kind of pull out some information. So what we saw is that the spread in histogram 2 from -50 to 100, I think it was, is much wider than histogram 1. So what we say, it has more variability in its data. Okay, so we're expecting kind of a broader range of values. Okay. So one way that I could, and it gets confusing, right? One, because variable and variability, and variable, it's all context dependent, right? So if I'm talking about a data set and I'm asking you, okay, so classify this variable, then of course that is, you know, a column in your data set. Whereas here, now we're talking about how variable the data is, and that's because it's changing. It depends on which thing you picked up and recorded some measurement of, because we're talking about numerical data, right? Then we'll switch gears to categorical. But right, so how variable is this data? So as an example, if we think about dogs in general, and we talk about maybe their heights, or let's be consistent because I'm using mosquitoes next, and so heights of mosquitoes is kind of hard to wrap your head around. But let's talk about the length of a dog, a wiener dog. So if you talk about the length of dogs and you're considering all types of breeds and whatever, uh, you're expecting a lot of variability in this data set, right? And so eventually where we're headed is, if there's a lot of variability, then a difference of 10, let's say, is not going to be that big, right? And so, whereas if you don't have very much variability, then a difference of 10 might be massive, right? And so it depends on the variability to determine if something is significant or extreme. We'll get there. But that's just kind of an appetizer. And now if you think about mosquitoes pretty uniform, right? We're not expecting a lot of variability or variation in the length of each mosquito. I go from 1 mosquito, 2 mosquitoes, 3 mosquitoes, 4. I couldn't help myself. And so the lengths of these mosquitoes are all pretty similar, right? And so so then if that's what I'm recording, then I'm expecting my variability in my data to be very small, right? And so even if I found a mosquito that was 1 centimeter longer than another mosquito, that would be a lot longer, right? That's like that's like double size. Whereas if you found a dog that was 1 centimeter longer than another dog, you probably wouldn't even notice, right? So that's where this variability is going to come into play. Let's talk about some non-normal distributions. And I'm just going to give you kind of the core 3, okay? And so we'll talk about distributions that are skewed to the left. So here I'll do left skew. I'll map these out first. Right skew. And then finally, we'll talk about bimodal. Okay. So if it's skewed to the left, meaning you have a negative, so you could say left or a negative skew, right? Either way, it's in kind of this direction, in the negative direction, or towards the left. Whichever you prefer, it's fine. So skewed to the left, the majority of the data is to the right, and the tail is going to the left. Now, I know for me, this is a little bit, or it was a little bit counterintuitive, right? Because we go from typically wanting to talk about, oh, well, most of our data is over here, okay? But now in statistics, what I want you to kind of start thinking about is, Well, in statistics, we're going to be more concerned with these extreme values, right? Oh, what's going on over here? A little bit mysterious, right? And so if you have a distribution that kind of looks like this, maybe, then you have a left skewed or a skewed to the left distribution. Whereas if you have a right skew, then it might look something like this, right? Distributions are skewed in the direction of the tail, okay? And so here, right, distributions are skewed in the direction of the tail, and so the direction of the tail is to the left here, and the direction of the tail here is to the right. Whereas a bimodal distribution, kind of anything goes. You could even have a multimodal distribution, but it's really only if you have distinct lumps of data, right? So you might have something that looks like this, right? That would be a bimodal distribution. Okay. A bimodal, bi means two, right? And mode we know is the number of peaks, right? And so we have two peaks, right, or two distinct modes for a bimodal distribution. If you find a bimodal distribution, it's likely that two groups have been combined, that maybe they should be analyzed separately, right? So if you kind of imagine if I had like one of those cool TV whiteboards, right? I split these, and now you have two normal distributions, right? Kind of smushed together here, but then cool. I have no idea how I could do that, but you get the idea. Okay, so if you find a bimodal distribution, you might want to hold off and maybe look at, okay, do I have, different groups here? Maybe these are from different years, same information, but maybe from different years. So maybe you should analyze those separately, right? There's information in there too that might be interesting, but yeah, something to consider. Okay, let me just. Okay, so we need to be able to describe the distribution just so we don't, well, mostly so that when you call your friend and you have to describe the shape, right? That's probably the newest part. Then really, as long as you stick to normal or non-normal, then you're okay, right? You don't. We'll come back to the skews, especially the left and the right skew. Bimodal we'll kind of leave in the dust. But the left skew and the right skew are going to come into play a little bit later. But in terms of describing the distribution, you can either say it's normal or non-normal. Right. So the reason we need to know the shape is because the shape is going to determine what can we do with this data, right? And also, what numerical measures should I be using for the center and the spread, right? So let's see here. I'll grab this whole, actually, let's just do this here for now. So I want to talk a little bit about that. Okay, so depending on if we have a normal or a non-normal distribution, our numerical measures of center and spread will be kind of shape determined, or shape dependent, I should say. So the center for a normal distribution is going to be the mean, so the average, right? Whereas the center for a non-normal distribution is going to be what's called the median. And what we'll do is, I'm introducing these terms here, but then we'll go through and we'll use an example where we actually go through and calculate all these things, and then we'll talk more about what they are. So, so for the center for a normal distribution, we can use the mean, which is the average, which we already know what it is. And I'm confident that you already know how to calculate the average of something. And then for a non-normal distribution, we'll use the median. Okay. For the spread, for a normal distribution, I like to use, for these intro courses, I like to use standard deviation because it's a little bit simpler. More advanced statistics courses usually use the variance, and we'll talk about the relationship between those two. And then for a non-normal distribution, we would use what's called the interquartile range. And again, I'll introduce that and I'll show you how to find it. But that's what we would use for the spread if you have a non-normal distribution. Okay, so remember, these are the numerical measures, kind of the more official measures, and that's why you don't have to spend too much time when you're just describing the distribution. You can just say, oh, it's centered roughly around 25. And then when you get deeper into it, then you can calculate the mean because you had a normal distribution, so then the mean is appropriate. One thing to note is that the median and the interquartile range, which we use for a non-normal distribution, can be used for any distribution. So they're kind of the jack of all trades here. But the mean and the standard deviation are more powerful, meaning we have more tools around it, more different types of analyses that we can do if we have a normal distribution, because then we can use the mean and the standard deviation. So if you have a normal distribution, then you're off to the races and you can use the mean and the standard deviation and the calculations that come with it. Okay, so what I want to do is just do a big example where we're going to work through how to find the mean, just in case you need a little refresher. Finding the standard deviation, that's a doozy. Finding the variance, okay, that's not going to be as bad. We are not going to construct a stem and leaf plot because I don't like them. And so we're not, it's in the notes. I kept it in the notes in case you wanted to refer to it. A stem and leaf plot is basically a poor man's histogram, but now computers are so, and computing is so cheap that we don't need stem and leaf plots anymore. But we are going to describe the distribution, and here I'll just say not doing, and use the histogram provided. So I've got it in the notes there. Oh, looks like I put it in the wrong place. That's okay. Okay. Then we are going to find the median, right? Which I introduced. I said, okay, if we have a non-normal distribution, we're going to use the median as our measure of center. And if we have a non-normal distribution, this dog is being very needy. Sorry, be right back. Although it doesn't change for you. Anyways. Okay, I'm back. Although anyways, still struggling with this whole pause business. Anyways, the interquartile range, right, is our numerical measure of spread for a non-normal distribution. So I'm going to show you how to find that and also what it is. And then we're going to talk about the 5-number summary, and also how to determine if there are any outliers. Now, we haven't talked about outliers yet, but you probably know what they are, right? They're just extreme observations that are outside the norm. And then we're going to make a box plot. We're not actually going to make it. We're going to look at a box plot and talk about the anatomy of a box plot, which is another way that we can visualize numerical data. So really, we're going to look at a box plot. That's more like it. Okay, so we're going to start with the mean, but first we have to introduce our data set, right? And so let's see here, chapter 1. So here is our example. Now, don't be scared. There is some R code in here, and even if we're not using R, there's nothing that says you can't be using it on the side. So that's why I included it in case you were curious and wanted to kind of play along. But if not, that's totally fine, and we don't need it. Okay. So the success of companies expanding to developing regions of the world depends in part on the prosperity of the countries in those regions. Here are the World Bank data on the growth in domestic product, GDP, percent per year for the period 2000 to 2004 in countries in Asia, not including Japan. I don't know, I just steal these from different places, and so here we go. We've got the country. Country would be categorical, right? But then we have the growth, the GDP, which is numerical, right? You can tell that it's numerical, but also it's a percentage per year. So it makes sense to talk about the average. And so I'm sold, it's a numerical variable. So the numerical variable is the one that we're interested in. And first thing I want to do is I want to count how many data points I have, right? And so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That is great. Making my sample size, oops, sample size is 12. Now the sample size, and I'm sure I have a note on it somewhere here, but the sample size is denoted by a lowercase n, and maybe I shouldn't have the equals there. The sample size is denoted by a lowercase n, and you're going to see that in any sort of report that you, oh, so silly. In any report that you read. So any study that's been done, they're going to report their n, and really what they're doing is reporting their sample sizes, right? And so that's a good one to get out of the way, just notation wise. Okay, so what we want to do is we want to find the mean GDP, the standard deviation of the GDP, the variance of the GDP, and so on and so forth. And then we want to describe the distribution of the GDP, and so on. Let's see here. Oops, wrong one. So I do have it all here. Sure. No sense in me writing it out again, I guess. Feels weird. So I'll start here. So we're going to find the mean, which means find the average. So what we're going to do is we're going to let x be a variable for the growth and domestic product, the GDP. So x bar is going to be the sample mean of the GDP, right? Because x is now a placeholder for the GDP. And so x bar, if I gave you these numbers without any context, right? So I'm only giving you these numbers and I asked you to find the average of them, what would you do? You would add them up and then divide by however many there were. And so that's why we started off and we counted out that there were 12. So that's exactly what we're doing, right? Except now I'm introducing this notation here that x bar, which is the sample mean, is the sum of the x's, meaning you add up all your x's and then divide by n. Okay. And so here, the sum of x, and this is a capital sigma, capital, or an uppercase. I don't know which is proper. Anyways, the sum of x, and so we read this as the sum of x. So all the values in x. And so summation notation, so this is called summation notation, is going to come up again. So it's going to be important that we're a little bit kind of, and I'm going to make this sigma look a little bit nicer, or try to. There. That doesn't look good, does it? Anyways, try to not fix it again. So it's the sum of x. You can see here what it should look like, what I'm going for. And then we introduced n, right? N is the sample size. So you read it as the sum of x, but it really just means, so the sum of x means add up all the values of x. Okay. So that is what we would do. And so I like to start with this example because we have that knowledge already of how we would calculate the average, and then we can link it to this notation that we're going to be using later on, right? And so here, the sum of all the x's divided by n. All right. I guess I talk through it. And these notes are thorough. I wrote them. I shouldn't be surprised. And so I've got it all here. I didn't need to write anything. I guess I should just read ahead. But anyways, so we add up all our x's. So the sum of x is going to be, once we add them all up, blah, 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 61.3. Hopefully I did that right. There's always room for mistakes. In general, if you find that I've made a mistake somewhere, that is very possible because I'm probably just calculating it on the fly. But in this case, I'm feeling pretty good. So the formula for x bar also introduces n, which we have already introduced just briefly here, right? But here it is in the flesh, which denotes the sample size, right? And we're going to use it a lot throughout the course, so it's a good one to become familiar with. So in this case, n is 12. So what we find is, it was on the next page. So what we find is, and we can kind of piece this together now, right? The sum of the x's is going to be replaced by 61.3 because that's what we found, right? And so kind of using this as a placeholder is going to be a good idea for when we calculate the standard deviation. You'll see 61.3 divided by 12, and I tried to be good about showing that this is an approximation, right? 61.3 divided by 12. Got my handy dandy calculator here. 61.3 divided by 12 is 5.10833 repeating. And so I've rounded it to 2 decimal places. So we've rounded our answer to 2 decimal places. So you should keep, so if this value was rounded, that would affect our final answer, right? And so in general, try to keep as many decimal places as you can. But if you need to use a result in later calculations, you can use the rounded answer. So in finding x bar, you shouldn't be rounding any values. But once you have x bar and you need to use it again, then you can use rounded values. It's weird, but you get used to it, right? And so there's kind of this double standard. Don't round, but you can round sometimes. So so the mean command is just if you have a data set called GDP, which we entered earlier in the notes, right? In case you're playing along in R, the mean of the GDP right, we find is 5.1083333333. Okay. If we have to find the standard deviation, let's see here. I'll just do this whole kit and caboodle. Or maybe not, there's no room. Crop top. Okay, maybe crop some more here. Okay. So finding the standard deviation, remember that a lowercase s is the sample standard deviation. So because we have a sample here, we don't have the population. What we are calculating is the sample standard deviation. So there are two common formulas. There are kind of variations, takes on it, but two common formulas for calculating the standard deviation. I'm going to introduce both, but I would probably lean towards the second equation. You'll see what I mean here. They're both just as scary here. And just as a reminder, do you remember what the sample standard deviation is? What's it doing? It's measuring the variability in our data, right? It's our numerical measure of spread for a normal distribution, right? So we're assuming we have a normal distribution. And so the standard deviation is our numerical measure of the spread. So this first equation is nice because it highlights that it's taking the distance from each point. So what this is saying is if we work inside the square root and then work our way out, it's the sum of each individual x minus the mean. So you take away the mean. So how far is each value from the mean, right? That's what that's saying. And then you square it, and then you add them all up, and then you divide by n minus 1, and then you take the square root. Breezy, right? Probably not really, but that's okay. Another option is to square each individual x and then add them up, and then that's going to be the sum of the x's squared. And then you already have x bar from earlier, which you can square and multiply by n, and then subtract that from the sum of the x's squared, and then divide by n minus 1, and then take the square root. We're going to do an example. But it might be good to do some practice. But what's nice is even if you're, making up your own data points, you can just Google a standard deviation calculator, put those points in there, and then just make sure that you're getting the same results, right? You'll see there's some wiggle room if you're using rounded values, but I'll highlight that. So like I said, the first equation is nice because it emphasizes that the standard deviation considers the distance between each data point and the mean. But ultimately, the second equation requires less work. This might be a nice time to introduce, or maybe a not so nice time, but the time to introduce the formula sheet, which is going to look very scary. And usually I don't introduce it this early on because it is so scary looking. I made it and I still would think so. So just, we're gonna go through it kind of line by line, and so it will all be okay. But let's see here if I've got it. Yeah, let's bring this over here. Whee. Whee. Okay. So is that 121, 124? Doesn't matter. All right, we're in chapter 1. And we have some, so I don't want you to look at anything else. Chapter 1. this is what you have for your formula sheet. I could have sworn I had both of these on here, but it turns out I can add it, but I probably will forget. Um, Notice that I only have the one formula for S, and that's okay. This is the one that I would encourage you to use. So, and it's the one that we're going to use. So, but you have the formula for X bar, which is the sum of the X's over N. We have the formula for S, the sample standard deviation. We also have the formula for IQR, which is Q3 minus Q1. Now, if only, so that's simple enough. If only we knew what Q3 and Q1 are, I'll introduce them. So then we're kind of back on easy street. This is probably one of the hardest calculations that we're going to do, one of that we're going to do this course. So let's see here. Let's get back to it. So what do we have to do to make that formula work? Well, if we talk about each component here, and I'm just going to drag and drop here, or paste, I guess, the rest of these. Oops. Uh-oh, I want to keep them on the same page. And be sneaky about it. They weren't meant to be on different tables. It just got chopped off. Okay, I could spend all night fixing these. And it is night for me right now. So there we go. Now I'm happy. Worth it, right? Okay, so if we talk about this formula here, let me just copy and paste it. What this is saying is that, okay, so you're going to need the sum of the x's squared, which really just means, okay, well then I need a column of each x. So square each individual x. And then sum. And then sum. I mean, and then add them all up. And so that's what I've done here, right? We've got the growth, which is your x. So each individual x, right? And then we found the sum of all these was the sum of the x's is 61.3. And then what you're going to do is you're going to make a new column beside it where you have each of these x squareds. So now you have x squared. So 5.2 squared is 27.04. Presumably, I'm just taking this thing or my notes words for it, I guess. 9.4 squared is 88.36, and so on and so forth. So each individual x is squared. Okay. And the sum of all that is 349.67. So now we know that the sum of the x's squared is 349.67. And we already know n is 12, so 12 and 12. Okay, we're off to a good start here. And also x bar is 5.11. So x bar squared would be 5.11 squared. Then multiplied by 12, bedmass, right? Exponents, multiply. I'm a math teacher, I should know this. Brackets, exponents, division, multiplication are on the same level. Addition and subtraction are on the same level. And if they're on the same level, you do them in the order that they appear. So let's see here. I've got the calculation in here. this is where it becomes important to recognize that, okay, well, this X bar, this 5.11, this was actually 5.10833 repeating, right? And so 5.11 is a rounded value, right? And so here, using the rounded value, will alter results slightly, not enough for it really to make a difference, typically, um, but it is something to keep in mind, right? And so what I've done is I've plugged in all the information that we found up here or stated up here. I've just plugged it into the original formula. And for me, you're not going to have to show a lot of work until test 2. But if you're showing work, and maybe scratch that, because that's only true for this next term. But anyways, so if you're showing work, now play. If you're showing work, I want to see the empty formula first and then plug in each of these values. And that's for me as the reader as well as for you, right? If you tell me that the sum of x's squared is 300 instead of 349.67, and then you plug that in, then that's less marks off than just randomly just jumping straight to this place here and saying 300. Then I'm like, where did that come from? Right? So you're always trying to guard your marks, right? And so just showing the empty formula is a good start. Another thing that I want you to try to do is to stack your equal signs. I don't want to see equal signs running across the page. That is just messy and bad, just bad habits. I do it sometimes, but usually it's if I'm running out of space on the page and it's like the last little calculation. Okay? But in general, try to stack your equal signs and start with your empty formula and then fill it in and then show each of the steps. So again, we end up rounding here from 1.817 to 1065 and up to 1.82. Now, if we were to use the mean and the standard deviation, these rounded values, we would have to keep in mind that, okay, these are rounded values, so they're not, exactly precise, but again, it's not going to make a huge difference. So what we'll find here is if we use software like R to calculate the standard deviation, what we would find is that it's actually 1.819819. And so that's slightly different than what we found here. That's okay, right? So this is a slightly different value than our result. But remember that our result uses a rounded value of X bar, whereas R is just able to keep all the decimal places and it can just do it. So I'm okay with these types of discrepancies, right? And so if you're doing a calculation and you have a standard deviation calculator, right, you can make up a bunch of numbers and try practicing the standard deviation, calculating the standard deviation, because it is hard and it's going to require some practice. And then just on your phone or whatever, find a standard deviation calculator, plug in your numbers, and then as long as these values are relatively similar like this, then you're safe, you're okay. So the next thing I want to do is find the variance. Now we've already seen it in that table that I introduced early on, but the sample variance is the sample standard deviation squared. And so we denote it by S squared. So the population variance is denoted by sigma squared, right? Same. So because we know S is 1.82, right? If we just square it, we can find the variance, right? So roughly 3.31. Notice that 3.3022545454, whatever, is basically what the variance is, right? And so the standard deviation takes the square root. So really what we're finding under the square root is the variance. And then when we square root it, we get the standard deviation. And then if we want to move back from the standard deviation to the variance, then we can just square the result and then we're back. And because we're rounding, we don't, it's close enough. So again, if you use software or Excel, whatever, SPSS, our answers are going to vary slightly, right? Or differ slightly. And that's because we've used the rounded value of X bar to find S, and then we used the rounded S to find the variance. And, but again, pretty minimal differences. Some disciplines, and like I said, definitely upper level statistics, if you go down that road, then you will start to use the variance more. And so we'll use the standard deviation in our calculations just because it's a little bit simpler. So here, construct a stem and leaf plot. We're not doing that, but like I said, I kept it in here because why not? What you're gonna do to make a stem and leaf plot is really, like I said, it's a poor man's histogram, and I've got a histogram down below here, but I just want to, I guess, talk you through it. You identify the stems, and so you put the stems, and then on the stems you basically put the leaf, which, so in this, so for Singapore here, the stem would be 2 and the leaf would be 9. Okay. So you set up your stems. So you identify the smallest stem and then the largest stem. I guess wouldn't matter, but and I think it goes to 9, but it got cut off on the page here, but that's okay. So you set up and you have to highlight all your stems, right? So 2 to 9, you don't want to skip any because that would be like closing a gap on a histogram, right? And so you want to have little parking spots. So here's where all your 2s go, 3s go, 4s go, 5s go. And if there are no 5s, then leave it blank and you can see that distribution. So what you do is you add the leaves. So when you write these by hand, which you won't have to do, but make sure that when you stack them, each leaf takes the same amount of space. Because what you're actually doing is you're basically building a histogram, right? But you have to kind of turn your head this way, kind of sideways, and then you can see, oh, each number is in a bin, right? So it's taking up the space. So this 9 is taking up 1 space in the 2 bin. The 2 and the 9 take up 2 spaces in the 3 bin. And so here, right, we can see the distribution here. It looks a little bit skewed to the right, but because we have such a small data set, I'm going to push for a normal distribution. Oh yeah, so for this reason, so now that we finished our stem and leaf plot, tilt your head to the side and you'll notice that we have made something that looks like a histogram. And so that's why I call it a poor man's histogram. But you can understand that when we didn't really have computers, this would be really valuable, right? It's not anymore. But for some reason, R and other softwares generate stem and leaf plots, but they do it a little bit differently. So they've condensed it because they've moved in increments of 2. But so it looks a little bit different, but again, you can kind of see the distribution here. So that was just a discussion on the stem and leaf plot. But so now we can describe the distribution. And I don't want you to use the stem and leaf plot. Use the histogram. Oh, I did it again. I meant to grab this here. Okay. So that was C notes for stem and leaf plot. Oops. Okay. And here is the histogram, which means I should probably grab the histogram. Okay, where is that little histogram now? Make it all fit on one page here. There. So to describe a distribution, right, we need to talk about the shape, the center, and the spread. So I'm going to go find that histogram. Here's the histogram of the GDP. Put it in here. So what I would say for this distribution, for the shape, now here's where things get a little bit murky. I've introduced the non-normal distribution, but so skewed to the left, skewed to the right, bimodal, anything. But really what we're going to end up doing is we're always going to be pushing for a normal distribution, mostly because then we can use the mean and the standard deviation, and it also opens up a lot of other analyses that we don't have, we can't use properly if we don't have a normal distribution. So we're always going to be pushing for a normal distribution. So what I do is, even if I have something like this, I can make two valid arguments. I have a really small sample size, so I'm very lenient with the shape. Or I can say, okay, well, it looks approximately normal with the exception of one outlier over here on the upper end, right? And so I have a couple of ways that I can kind of sweep it under the rug, so to speak, and still pretend that I have a normal distribution. If it's clearly not normal, then of course you can't say that you have a normal distribution. But in general, we push for a normal distribution. Okay, here, I'll fix this. Looking at the histogram and the stem and leaf plot. You can use the stem and leaf plot because we have it. We would say our distribution is approximately normal with the exception of one outlier. And because we have the data set, I can look back and see, okay, well, what was my largest value? It was China. So then my outlier is China. And here, notice that I'm hesitant to say it's skewed to the right. If the outlier was much more extreme, then I would say that the distribution is skewed. But whenever we can argue that our distribution is normal, it opens up a much larger set of tools that we can use. So I'm going to highlight that because that's what I was saying earlier. Okay. So for the center, I would say it's around 4 or 5. So looking at the histogram here, right, maybe 4.5, 5-ish, right? Somewhere between 4 and 5. It looks like you kind of have to look at how these are broken up, 4 and 6. So 5 would be here, somewhere between 4 and 5. Great. That's going to be our center. And so we don't need to be precise with the center. We just need an idea of where most values would fall. You could even say something as vague as somewhere between 4 and 6. That's fine. As long as you've got kind of a reasonable range. And then the spread is just a rough eyeball, quick approximation, which is really just the maximum and the minimum values. And then knowing a range of reasonable values will help us determine if a value would be considered extreme or not, which is what we're going to be doing later. Okay. So looking at the histogram, we would describe it as the shape is approximately normal with one potential outlier on the upper end. The center is around 4 or 5-ish, and the spread is from 2 to 9. So let's have a look here. Yeah, so from 2 to 9 or 10. 9 or 10-ish. Right. Rough approximations. Okay, good. So here, the 9 was from the stem and leaf plot, because then we had the actual data points. Here is the description for the histogram, but that's what we corrected it to. Okay. Okay, so the next thing we want to do is find the median. And I'm just going to grab this here. Put it on the fresh page. So finding the median is pretty fun. And so the median is the value that splits your data in half. Now, it can be a data point, or it might be the average of the middle 2 data points. And that's confusing because the median is also a center, a measure of center, and so is the mean, right, the average. And so using the average to find the median is a little bit of a, I don't know, mind bender, but that's okay. So the smallest 50% of data points are below the median, and the largest 50% of the data points are above the median. So to find the median, what you're going to do is you're going to sort your data from smallest to largest. Here you're going to check in and make sure, so you count how many data points you have. We know we have 12, right? So once you've sorted them, you should probably make sure that you have 12 data points, otherwise it's not going to work. And then you use the patent pending boop, boop, boop method. It's not patent pending, but I do think it's funny. So I call it the boop, boop, boop method. That is not, I don't think you'll find it on the internet anywhere. I just call it this. And so there are more sophisticated techniques for finding the median, but this, for our size data sets, it's definitely the easiest. And so I do have a little footnote here. So I use these simplified steps in finding the median and the quartiles. We'll use the same method for the quartiles. When technically we would say the position of the median is n/2 for odd sample sizes and n+1/2 for even sample sizes. But notice that this only gives you the position of the median, and then you still have to go and find it. So that seems really kind of blah for me. So here's our sorted data. It was sorted for the stem and leaf plot, so that's why it says again. So from smallest to largest, we've got these sorted. And what you're going to do is usually we've got our data points on a lined piece of paper here. But so what you're going to do is you're going to put your two, well, you can put whatever fingers you want or whatever things you want, but start from the outside and then just boop, boop, boop your way into the middle. And you're either going to land on one value or on two values. If you land on two values, you're going to circle them, draw a line through, and that line is going to be the average of those two values, and that line is going to be your median, right? It's easier if we just land on a value. But for us, I'm going to pause this and jot this. Okay, so I've jotted these down, and like I said, just always make sure we know we have 12, and so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Phew. Okay, good. So now this is a little bit easier to deal with than kind of you can, but let's see what we get here. Okay, so I'm going to put both my index fingers here and boop my way in. So one, boop, boop. Oh, I tend to lose. I have a hard time, so I usually have to start over. So boop, 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 boop. I'm landing on these two, but I'm just going to confirm. And what you can do is you can confirm by going 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It all checks out. Okay, so I've circled these two that I landed on as my middle value. And then I draw a line through there, and the median is going to be that line. So the median is 4.6 plus 4.7 divided by 2, which last time I checked should be 4.65, right? Okay. So that would be your median. Okay. As a second option, right, consider the same data set with 9.4 removed. Now what I'm going to do is I'm going to cheat, and I'm just going to copy this here. So then this is no longer my median, and I've removed 9.4. So now if we go ahead and find the median here, what we're going to find is we're going to land on some value, but let's do it. So 7.3, 2.9, boop, 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 boop. So then here, in that case, the median is 4.6. So slightly different answers, right? Depending on how many data points you have. Good. Okay. So that's how you find the median. And notice it just cuts your data in half. I guess I'll bring this in here, but we don't actually really need it because we already did it. Right? Oh, maybe I'll put it over here. Oh my gosh. There. Okay. Sorry, just got distracted doing cleaning up. Anyways, so like I said, if we remove one data point, like the 9.4, man, it's like I knew this. Okay, or like I always do the same thing, I guess, we would find that we land on one number. So that we would circle, and then that would be our median. And then I do walk you through how to create a new data set with the one removed. Oops. This one. First, you need to create a new data set with the last point removed. And so I just removed the last point, and then the median is 4.6. The reason we use the median and the interquartile range later for non-normal distributions is because they're resistant to outliers, whereas the mean and the standard deviation uses the mean, right? So of course it's going to be influenced, but the mean is not resistant to outliers, meaning that it's going to be pulled towards extreme values. Okay. So if the mean and the median are roughly the same, we can usually assume that we have a normal distribution. So this little tidbit, I'll follow up with a little graphic here. So if you have a normal distribution, and here the mean is not resistant to outliers, meaning it will be pulled towards extreme values, which means in the direction of the tail. So you might have a distribution like this. Maybe it's like this. Okay. Skewed towards the right. And we'll put kind of the median might be somewhere here. Whereas the mean would be somewhere here. So the mean will be pulled in the direction of the tail. In the direction of the tail. Okay. So then I want you to think of the other situation, right? If you have a normal distribution or even a symmetric distribution, but often if you have a symmetric distribution, it is normal. If you have a symmetric distribution, then there is no tail for the mean to go to. And if it's symmetric, then the median would be in the middle. And so if the mean and the median are roughly the same, then we can usually assume that we have a normal distribution, right? And so, whereas here, if we think about, try my best here, a normal distribution, the median would be here. And it would be kind of equal to the mean. Mean, median, mode. Mode, remember, is the highest peak of data. So if you have a normal distribution, then the mean and the median and the mode are all the same. Okay. But usually I just focus on the median and the mean because they're calculable. Is that a word? I don't know. But that's something to keep in mind, right? The mean is always going to be pulled in the direction of the tail. So if I told you that the mean was 4 and the median was 16, what's the shape of that distribution, right? Okay, so for a quick example, just so we can kind of flex our knowledge here, if the mean is 4 and the median is 16, what does that distribution look like, right? Well, the median is where the lump of the data is. So at 16 here somewhere, I have the lump of my data. Whereas over here, maybe at 4, I've got my mean. So it might look something like this. Now I'm just making it up as I go. But so here, right, if the mean is less than the median, what we're going to find is that it's being pulled towards the smaller values, so it's skewed to the left. Skewed to the left. Oops. Okay. How about the interquartile range? Oh, that's a lot. So the interquartile range, it does use the quartiles, of course. So let's see here. We need to talk about the quartiles first. So the interquartile range, or the IQR, is the distance between the first and the third quartiles. Now, the first quartile, we denote by Q subscript 1 or Q1, means that the lowest quarter, right, or 25% of the data is below this value, and 75% of the highest values are above it, right, or 3/4. Right, so that's where quartile comes from. The median is actually the second quartile because it splits it into 2/4 and 2/4, half and half. Right. Q3 is the third quartile, and it has the lowest 75% below it and the highest 25% above it. And so the quartiles are special cases of percentiles. Now the pth percentile has p% below it and 100 minus p% above it. Okay, and so that's going to be good to remember. Often, the most common thing that we talk about on percentiles is maybe test scores, right? Or usually it's like baby measurements, like baby weights, that type of thing. Always measuring in the 90th percentile. What does that mean? The 90th percentile means that you have 90% below it and 10% above it, right? And so it's really just a way of saying that you're in the top 10%. Right? So remember that about the percentiles. But Q1 and Q3 are the most common percentiles that we're going to talk about. So how do we find these values? Okay. We're going to use the same method as we did for the median. So the boop, boop, boop method. I want to boop, boop, boop. One little thing is that depending on if we took the average of two values, so the 12 data points in our example, or if we landed on a specific data point like we did with the 11 data points in our example, finding the quartiles will depend. Okay, either way, you're going to start at the median. And so let's first look at the one with 12 data points, and then we'll look at the one with the 11 data points and see how they differ. But basically, you're going to start at the median and then only focus on the lowest half for Q1 and the upper half for Q3. And then use the boop, 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 boop method and count your way in. Okay, so I'm going to copy these points here. Copy all of this here because I can. Okay. So first thing I'm going to do is look at this full data set with all 12 points, right? And so because the median is here at this line, I should use 4.6 to start my boop, boop, boop for Q1. Okay, and so if you've used the value as the median, so the 4.6 here has been used as the median, then I can't use it anymore. Then I would start here at 4.4. So that's the difference. But like I said, either way, you're going to start at the median. Either it's neither one of these values specifically, it's 4.65, somewhere here at the line, or it's been taken, then I start to the side of it. So in this case, the first one, if I boop my way in here, so boop, boop, I find that Q1 is 3.9 plus 4.1 divided by 2. And let me just confirm here, 3.9 plus 4.1 divided by 2. It's a beautiful 4. Great. Doing the same thing for the third quartile, which is on the upper end here, starting at 47 and 94, I can boop my way in, and again, Q3, remember Q2 is the median, but we'd call it the median rather, is going to be 5.4 plus 6.2 divided by 2. 5.4 plus 6.2 divided by 2 is 5.8. Q3 is 5.8. Whereas now, if we consider this altered data set where we removed the last point, right now I've used 4.6 as my median, and so my booping would start at 4.4 or 4.7 depending on which way I'm going. So 4.4 and 2.9, oops, if I boop my way in here, I land on Q1 equals 3.9. And same thing here, I boop, boop, Q3 is 5.4. Okay. They're similar, 3.94, 5.4, 5.8, right? And that's kind of how it's going to go. I've got the calculations here. Where did I copy to? Okay. I wanted it to not take up so much room, but that's okay. So we find these quartiles, and then what we can do is we can find the interquartile range. Now, the interquartile range, we already saw it on the formula sheet, is just going to be Q3 minus Q1. Remember, the interquartile range is the distance between the two quartiles. And so if you did Q1 minus Q3, you would get a negative number, and that's not very nice. And so if you want to find the distance, right, you would take the largest value minus the smallest value. And so that's what we're doing. So one thing that I will say is if you're following along in R, then it uses a slightly more sophisticated method than the boop, boop, boop method. And so you will get slightly different values. But for homework and for, just questions in this course, I am expecting you, because I'll be giving you small data sets, so I am expecting you to just use the boop, boop, boop method. Okay. But it does give us the quantile information. And I'll just bring in all these notes here. And you know what? I'm going to crop this. So I've got the descriptions there, but if you were able to follow along and the boop, boop, boop method kind of works for you, then you can ignore the text there. But okay, so we found the quartiles, also the quantiles, I guess, kind of the same. So you can use R to find any percentile, right, by adding it to the quantile command. Just kind of, it's possible. So anything that you need to do, of course, is possible, but we'll parking lot that for now. So we are able to find the interquartile range for both of these data sets, right? The shortened one and the original one. So the next thing I want to do is I want to find the 5-number summary. Once you have calculated or found the median and the quartiles, the 5-number summary, you're on easy street. The 5-number summary is a list in order of the minimum, the first quartile, the median, the third quartile, and the maximum, right? Notice we're increasing, or you could go in decreasing order, but I like to go from, I like to be increasing. So starting at the minimum, going to the maximum, but they have to be in order. Otherwise it doesn't make sense. For a data set with 12 points, so the original data set, our 5-number summary would be the minimum is 2.9. Now here's where having the data sorted, those are just kind of gimme points, right? Finding the minimum and the maximum, you just look at your data set once it's sorted and you pick out your minimum and your maximum and then you're done. 2 out of 5, done. Q1 we found was 4. The median we found was 4.65, and Q3 we found was 5.8. So often what I'll do is I won't ask you to calculate the quartiles or calculate the median. Instead, what I'll do is I'll ask you to calculate the 5-number summary, which implies having to find the median and the quartiles. Hey, it's like I've said this before. Often I'll simply ask for the 5-number summary, which will require that you find the median and the quartiles. So, are there any outliers? Start here. Seems like an easy enough question to answer, right? Are there any outliers? But what we're going to do is, and what's very common, is that we're going to use the 1.5 IQR rule to find outliers. Now the problem becomes, okay, so when I look at that histogram, for example, going back up there, sorry, it might lag a little bit here, but I think it's worth it. Let it catch up. Okay. So remember when I described this distribution, I said it's approximately normal, maybe with the exception of a potential outlier over here. Now, what we need is some sort of threshold where, okay, if you're past this line, you're considered an outlier. If you're inside this line, then you're not considered an outlier. And that can happen on the lower end as well, right? And so we're going to have these bounds, a lower bound and an upper bound, where anything within these bounds they're fine, right? But anything beyond these bounds will be considered outliers. So we need some mathematical way to approach this. And I saw it there. And it's called the 1.5 IQR rule. And so students have asked me before, right, why is it 1.5? I just don't understand why it's 1.5. And it just is. That's what's been agreed upon. And that's the most commonly used method. You could use 2. I think 1.7 is a thing, but just generally 1.5 is just accepted. Um, so there are other methods out there, of course. People have to get their PhDs somehow, right? Oh, I've got this new method of finding outliers. Uh, yeah, anyways, 1.5, that's what we're going to use. So what we do is we take the interquartile range, which is the distance between the quartiles. We multiply it by 1.5. And then what we do is we take that distance from each of the quartiles, and then those will make up our upper and lower bounds. So the 1.5 IQR rule says that any values that are beyond a lower or an upper bound will be considered outliers. So the lower bound, and notice the lower bound is Q1 because I'm going from the first quartile and then I want to move down 1.5 times the interquartile range, which means that I have to subtract from Q1. Whereas the upper bound, it got cut off here, but you can probably figure it out. The upper bound is Q3 plus 1.5 times the interquartile range because I want to go up from Q3. So I'm going to highlight these differences because I want to move from the quartiles and out, right, respectively. So, I'm gonna just grab this whole thing and hope it does not fit. Okay. I tried to kind of mini-me, you complete me here, but I don't think it's gonna work. So I'm just gonna crop it. Okay, so in the data set with 12 points, we suspect 9.4 might be an outlier. So we're gonna calculate the upper and the lower bounds to determine if there are any outliers, right? So we find the interquartile range is Q3 minus Q1. And so in this case, it's 5.8 minus 4, which gives us an interquartile range of 1.8. And so in this case, the lower bound, which is Q1 minus 1.5 times the interquartile range, 1.5 times 1.8 is 2.7. So 4 minus 2.7 is 1.3. So what you're going to do is you're going to go to the data set and have a look, right? Draw 1.3 on there. And I'm going to grab it here and build on this. You don't need to keep writing it out. You can just do it once. Now you tell me, right? Oops. I don't know. Okay. So what we're going to do, right? This is the interquartile range for when we had all the data points, right? So now we're only looking at this data set with all the data points. So what you're going to do is we're going to draw 1.3, and notice that because we've sorted these from smallest to largest, right, 1.3 would be down here. So here's our lower bound. equals 1.3. Notice that there are no values beyond this point. Even if you just had the minimum, you can compare the minimum to the lower bound. And if the minimum is larger than the lower bound, then there are no outliers on the lower end. So since there are no values smaller than 1.3 in our data set, there are no outliers on the lower end. So that's how you would justify it. Now let's look at the upper bound. So again, 1.5 times 1.8 is 2.7. We already showed that worked, so I can just jump straight to 2.7. And so 5.8 plus 2.7 is 8.5, making my upper bound. So if I put 8.5 on here, it would be somewhere between 7.3 and 9.4. So the upper bound is 8.5. Okay. So now what we're going to say is that since there's one value, 9.4, beyond the upper bound, there's an outlier on the upper end, right? So therefore, there's one outlier in total. Whereas now, let's have a look at, oh, I only did the one. Okay, let's do the other one. Right? Or maybe here, you take a moment and pause this and you try to figure out what the upper and the lower bounds are for this altered data set without the 9.4, and then I'll meet you back here. Okay, so first thing we have to do is we have to find the interquartile range. So in this case, the interquartile range is still Q3 minus Q1, but it's going to be 5.4 minus 3.9. 5.4 minus 3.9 puts me at 1.5. So then my lower bound is Q1 minus, because now I want to go down 1.5 times 1.5. Ugh, that's confusing, but that's okay. Minus 1.5 times the interquartile range, which is, so now Q1 is 3.9, right? So 3.9 minus 1.5 times 1.5. Hopefully I did that calculation right. Anyways, 1.5 times 1.5 is 2.25. So 3.9 minus 2.25. Now that I've shown that that's what it becomes, I can just skip right to 2.25 in the next calculation. But 3.9 minus that is 1.65. I'm going to scoot this over and try to keep it on the same page here. So up here, again, 1.65 is less than 2.9, so it's going to wrap around all the lower data points here. So lower bound is 1.65. Notice that because the interquartile range is different for each of these data sets, right? That's why our numbers or the lower bounds and the upper bounds are slightly different depending on what our interquartile range was. So the upper bound is going to be Q3 plus 1.5 times the interquartile range, which is Q3 is 5.4 plus 1.5. I'll just do it again, times 1.5, which is 5.4 plus 2.25. 5.4 plus 2.25 puts me at 7.65. Now, if I look here and I have 7.3 and 7.65, 7.65 wraps around 7.3. So in this case, the upper bound is 7.65. And so now I can see that therefore, uh, since no values are beyond the bounds, there are no outliers. Bink. Right. Okay, so we're on to the very last thing that we want to do for this example, and that's make a box plot. We're just going to look at a box plot and talk about the anatomy of a box plot from Boston. Um, so I'm going to bring in these rules, these guidelines here. You're not going to have to draw a box plot, but it's good to know kind of where everything came from. So a box plot is essentially a visualization of the 5-number summary. So and it includes a graphical representation of outliers. So that can be handy, right? We can draw a box plot, or we can generate a box plot, and it'll highlight if there are any outliers and which ones they are. So you're going to have to determine the appropriate axes, or it'll be given to you if you ever had to draw it, but probably not. What you're going to do then is you're going to draw lines at the median, the first quartile, and the third quartile, so the middle values of your 5-number summary. And then you're going to connect those lines of the quartiles to make a box with a line in the middle. And I'll show you what I mean in a second here. Then you're going to temporarily draw lines at the lower and the upper bound from the 1.5 IQR rule. But then the lower whisker is going to go to the smallest value inside the bounds, right? So for example, might make more sense once you've seen what a box plot looks like. But for example, here, the smallest value inside the bounds would be 2.9, and the largest value inside the bounds would be 7.3. So that's where we would draw our whiskers to. Cute, right? Whiskers. Let me bring in the box plot and maybe it'll make more sense. So this is the whisker, and this is a whisker. So a box plot is just a box with the middle 50% of your data in the box, right? Because this here is your median. Oops, maybe I shouldn't. This is the median. And here's your, and it depends on which scale you're using. So often, because I like to draw kind of on a number line, and so often I'll tilt these, flip them this way, and then draw my lines, and you can draw your box going horizontally instead, and that's totally fine. Usually software, they like to generate these vertical box plots, and it takes up less space. But if you're drawing it by hand, then it's easier if you just have a number line and then you draw your lines that way, but that's okay. So the middle line is the median. And then we've got the Q1 here and Q3 here. And then what we said was you extend the lower whisker. So backtrack one step. You're going to temporarily draw lines at the lower and the upper bound. Okay, so this is with all the data points included. And so let's see here. This would be your upper bound for the 1.5 IQR rule. Now there's no data point there, and so you'd have to drop it down to the low, or the closest data point within the bounds. Okay. And so that's what it means when it says temporarily draw the lines at the lower and upper bounds from the 1.5 IQR rule, and then extend the lower whisker to the smallest value inside the lower bound. And then any outliers are indicated by uh, an asterisk or just a dot, right? So here, this is an outlier. Okay. And then same thing on the upper bound. Extend the upper whisker to the largest value inside the upper bound. And then any outliers are indicated by a star or a circle in this case. So in this data, because we're graphing the full data set, this whisker should be at 7.3, right? And this lower whisker should be at 2.9. So here, 2.9, and this whisker should be at 7.3, right? Because those are actual data points from our data set. Okay. Okay. I don't want to spend a lot of time talking about categorical data because we're going to parking lot it for a long time. And so until chapter 6, essentially. So I just want to talk bare bones here. But for categorical data, to visualize categorical data, we're going to use a bar graph. Okay, or bar plots. There's lots of things we could call them, but notice that now I'm talking about categorical data. Okay. I guess I should introduce the data set that I'm about to be talking about. So the MT cars data set is quite famous, and we use it a lot because it has all these kind of relatable variables, and it's good for practicing if you can identify numerical variables, categorical variables, and just kind of it's a good data set to work with. So to visualize categorical data, we commonly use bar graphs or pie charts or even donut charts, but I'll talk about that later. Pie charts are popular data visualizations. We should only use bar graphs for visualizing categorical data. Okay. And the reason for that is that we should use bar graphs because even small differences are detectable. Whereas a pie chart, and I've got an example, you can't see those. So if there's really anything that you take away from this course, or at least this lecture, let it be that you're not going to make any pie charts ever again. And you can look down on people who do. No, and then donut charts are just kind of this weird, it's a pie chart with a hole in the middle. It's weird. People think they look cool, but they don't. So anyways, so I want to see bar graphs. Okay, so we should only use bar graphs for visualizing categorical data. Okay, so we're going to look at an example that uses the MT cars data set, and it has a little, oops, I guess that still works, but it has a little description here on the data set on the side, but it's just cars data. And so we've got the miles per gallon, the number of cylinders, the displacement, who knows what that is, the gross horsepower, the rear axle ratio, the weight, the quarter mile time, the engine. It can either be V-shaped or straight, who knows, whatever. The transmission, 0 is automatic, 1 is a manual. So in your data set, you're going to have zeros and ones, and those zeros and ones are um, are really your categories, right? For the engine, 0 means that it's V-shaped, and a 1 means that it's a straight engine. I don't know. And then gear is the number of forward gears. Okay. Oh, and then it got cut off, but the carb is the number of carburetors. So usually, because we have categorical data, usually what we end up doing is to summarize categorical data, we use a table, right? It's not usually this kind of robotic looking, but this is generated in R, and it is a table, so that's okay. So we're going to consider the first categorical variable in the data set, which is the number of cylinders. So we can summarize the cylinder variable in a table, which shows the counts of cars in each of the 3 categories. That's really all we can do for categorical data. So we have 11 cars that have 4 cylinders, 7 cars that have 6 cylinders, and 14 cars that have 8 cylinders, right? And so that's information. Okay, cool. We can visualize that. And like I said, we can use a pie chart or a bar chart. And let me see if I can get all of this on the same snag here. Okay. So like I said, we can read the table, but people don't like reading anymore, right? And so, or we never have. Who are you kidding? So you can make a pie chart, but the problem is that it's not immediately obvious which slice is larger, right? If we kind of look at it hard, we would probably pick the 8 slice as the largest. Whereas a bar graph is exactly what you think it is. It has a bar that represents the height, which is the height represents the count in each category, right? So 4, there were 11, right? So that matches our table. So the bar graph is really just a visualization of the table summary of the data, right? And so now it's very obvious immediately when you look at this that 8 has the highest count, right? So it's the most common in this case. Now, that is the reason why we should be using bar graphs instead of pie charts, right? Because if we go back to our number 1 rule for data visualization, well, it should be straightforward, right? When you look at it, minimal explanation. Maybe you'd have to talk about, the data set so people know what it is you're showing. But in terms of which group has the highest or the smallest count, it should be obvious right away. And so that's why we should be using bar graphs instead of pie charts. Let me see here. I'll bring in. I want to bring in the rest of this little blurb here. Okay. So in the pie chart, you might think about adding labels to the slices to help you identify the smallest slice or the largest slice. But like I said, that works against the principle of data visualization, where the goal is to have a clear and concise visualization. The only time that a pie chart is obvious is when there are only 2 categories. Okay, But if we take a step back, we shouldn't be making pie charts with only two categories, because if I told you that uh, 30% said yes, how many said no? Probably 70%, right? And so if there are only two categories, yes, no in this case, then knowing one means you know the other, right? And so then knowing the count or the percentage in one category means we know the count or the percentage in the other category, which essentially eliminates the need for a visualization, since you can just say the one number, right? Um, or, what's the probability of you getting an A in this course? It's 70%. I don't know. Then what's the probability that you don't get an A on this in this course? 30%. Why am I going for 30, 70 all the time? Anyways, but that's something to keep in mind, right? So you don't want to have just two categories. Oh yeah, here I have a little example. Another vague example. The percentage who agreed with a statement in a sample was 43%, implies that the percentage who disagreed with the statement in the sample was 57%, right? Notice we're talking about the sample, but that's okay. Okay. So for the rest of these notes, I'm just going to quickly highlight. We're not going to spend a load of time here because, like I said, this doesn't come back up until chapter 6, and that's a ways away still. So I'll bring it up when we need it later on, but I'll still go through it. But so categorical data is often summarized in a table, as we did earlier. So we can make frequency tables of the first two categorical variables, which are the cylinder and VS. VS was the V-shaped or the straight engine. So, right, we have a frequency table. So this is a frequency table. Okay. Because it shows you the frequency that you have in each category, right? And then you can make a frequency table of the V-shaped or the straight engine. There are 18 V-shaped, 14 straight engines. Often we're going to be more interested in how two variables relate to one another, right? And so what we can do is we can map so here, this is our VS, and here, this is our cylinders. So now what it's done is we've made this contingency table. It's called a contingency table is a table that summarizes data for two categorical variables. And so it doesn't matter which one goes where in most cases. And so whichever way you want to do it is fine. But there's one car that has a 4-cylinder engine and is a V-shaped engine. There are 14 cars that have 8 cylinders and a V-shaped engine. So what does that kind of make us think about? Okay, so it looks like it's more common for an 8-cylinder engine to have a V-shaped, right? And then look here, for the 8-cylinder engines, there are actually 0 that are straight. So so that's information, that's valuable information that we might use, right? So we've used the raw counts, but in general, when we're reporting on categorical data, what we should be doing is use the proportions, right? Because when I say 14, 14 doesn't mean anything, right? 14 out of how many? And so that's what the proportion is. So a proportion is the number in a category over n, right? And so I've got the proportions here. Oops. Okay. What's going to come up later is the proportion is a percentage. It's just a proportion. So a percentage is a proportion multiplied by 100. So here, right, 0.03, we're in this shared category of 4 cylinders with a V-shaped engine, right? And then 0.3125, which would be 31.25%. So see the relationship between a proportion. So these are all proportions. And then if I multiply it by 100, I get percentages, which we're much more familiar with, right? And reporting we usually do in percentages. And so now, right, now we can see 14 as a count. Well, it's way more valuable to know that 43.75% of cars that have 8 cylinders have a V-shaped engine, whereas 0% that are 8 cylinders have a straight engine. So that's just something to keep in mind. So when we're considering more than one categorical variable, we can combine information in a single bar chart. So there are kind of 2 common options. We could do a segmented bar chart, and I'm pretty sure I have an example here. Yeah. You can do a segmented bar chart or a side-by-side bar chart. Okay, so the segmented ones, sometimes if you have proportions, they'll add up to 100%, all of them, and it'll just show kind of oil and water style, which segment is for which, and of course we'll have some legend somewhere. Or you can have side-by-side bar charts where you have the 0, which is the V-shaped engine, and 1, which is the straight engine. So we've lumped these bar charts together, and then we show how many cylinders there are in each of these categories. So I think this is the last thing we'll see, I guess. But the last thing I want to talk about, I want it to be the last thing. How about that? No, that's not what I meant. But so now I want to talk just briefly about what do we do if we want to compare numerical data across groups, so across categories. Okay. So if we want to visualize the distribution of a numerical variable, miles per gallon, for example, by a categorical variable, we can use what's called a side-by-side box plot. And man, am I psychic or what? Let's look at the miles per gallon by the cylinders. So if we make a box plot of the miles per gallon by the cylinders, what it ends up looking like is this. Oh, and then I've got my funny here, which I'll bring in, don't worry. But first I want to talk about this. Okay, so notice that now I have these box plots, right? But I've broken it up. The miles per gallon is broken up by how many cylinders I have. So what can we learn about the miles per gallon? So they're all on the same axis here, and that makes them comparable, right? Now we can compare. And what we see is, well, the four-cylinder cars have quite a high miles per gallon, whereas, and it seems to be decreasing as we increase the number of cylinders. 8 miles per gallon definitely has the lowest miles per gallon, so lowest fuel efficiency. Um, what else can we talk about? Depending on how much overlap there is with these boxes or the box plots, if there's not very much overlap, then we can go ahead and say that there's a large difference here. So between the four-cylinder and the six-cylinder and eight-cylinder, the four-cylinder, almost all the data is all above everything in the 6 and the 8. Definitely the 8, but most of it in the 6. It's hard to draw this line across here, but right. And so then we can say, oh well, most of these of the data from the four cylinders, it's the miles per gallon is potentially significantly higher, right? And so that's where we're going to take this. But now I just want to end it with just one little funny here from How I Met Your Mother. Marshall made a pie chart of his favorite bars and a bar chart of his favorite pies. And on that note, chapter 1, done. Mic drop. Well, Apple pen drop. Nice work.